So for that, there is for that there is a Chinese there was a Chinese professor, in fact an electrical engineer, who thought of this Maclaurin series as a transform. Okay, Maclaurin series as a transform. So I just write that for you. I'll come back to this later. So what do I have? Y of x is summation n equal to 0 to infinity, or I'll take this to be k. Okay, 1 by k factorial dk by dx to the power of k, y of x is this Maclaurin series. Okay, it's Maclaurin series, right? So I've just written it in summation form. Now let us see this. Okay, let us see this. So by differentiating y of x k times and then scaling it by k factorial and evaluating at x equal to 0, what am I getting? I am evaluating at x equal to 0, so it is independent of x. Okay, so it means it is dependent on only k. Okay, is it dependent on k? Because I am evaluating at x equal to 0, this entire thing depends only on k now. So that I will suggestively write it as y of k. Is that clear? So let me write that. So I'll take y of k. What is y of k? That is 1 by k factorial dk by dxk operated on y of x evaluated at x equal to 0. Okay? So you see here the notion of a transform. Y of x is transformed to y of k, capital Y of k. Okay? So how did I get this? How did I get this? I differentiated the function k times and then scaled by k factorial and then evaluated at x equal to 0. So all that entire process of differentiating, scaling and evaluating at x equal to 0, I will simply write that as d of k y of x. Okay, I'll just write it like that. So what do I get now? I take the differential transform. I take the differential transform of y of x, and what do I get? I get another function which is y of k. So here is the notion of a transform. Now suppose you take Laplace transform or Fourier transform or any transform which you have studied, what are the properties you look for? Linearity property, okay, you name it, you can see there in the case of Laplace transform. So those properties which you have in the case of Laplace transform, you can see that in the case of this differential transform. Okay. So now let us see. I'll write this now. For this I'm going to write y of k. So let me write that. So I have y of x that is equal to summation k equal to 0 to infinity y of k into x to the power of k. So what is this? I am getting back my y of x. From the transformed function y of k, I am getting back my y of x. So the notion of an inverse differential transform. Is that clear? So you have the notion of an inverse transform here. So this is inverse differential transform. Okay? So I told you, generally you verify a few results, some theorems, linearity property, you name it, that can be verified for this particular differential transform. Now what I'll do is, I'll just take this result, elementary result, I'll take this and see whether it is useful in obtaining the solution of that equation. Okay, so let me quickly do that. So what I'll do is, I'll find the differential transform of dy by dx. What is it? I have 1 by k factorial dk by dxk. I'll just use first principles. Dy by dx at x equal to 0. Okay? So what happens to the derivative now? The kth derivative becomes the k plus 1 the derivative. Is this fine? Okay. So when I had that is 1 by k factorial dk by dxk of y of x evaluated at x equal to 0, I wrote that as yk when everything was k. So now what do I have here? K plus 1. So what can I write this to be? K plus 1 I take it out. So what I get? Yk plus 1. Okay, as simple as that. So now you can easily guess. Suppose you want second derivative. What are you going to get? K plus 1 into k plus 2 into y of k plus 2. As simple as that. Okay? I think I'll use this, I'll write this again. I'll require some results. You should tell me the answer for this. Differential transform of x to the power of n. Okay. M equal to k, what do you get? Use first principles. 1 by k factorial will be there. Now m is k. I am differentiating x to the power of k how many times? K times. So what do I get? K factorial. So 1 by k factorial into k factorial evaluated at x equal to 0. So that is 1. Okay, so when m equal to k, I get 1. Okay? And m less than k, what is it? M less than k. 0. You differentiate x squared with respect to, 3 times. So the this is 0. Now the important thing is m greater than k. What is it? What happens when you have m being greater than k? Now suppose I take this. I have say x cube. I differentiate twice with respect to x. So I will have an x remaining. And now I am evaluating at x equal to 0. So what happens? It is again 0. So when I find out the differential transform of an algebraic function like this, so these results are obvious. Okay? So this is what you have. So next, okay, we'll take this. Okay, this can normally be proved by mathematical induction. You can first put for 1, then 2, then k plus 1. So I will quickly write down how to go about doing this. I just take k equal to 1. So I have d of f of x, g of x. So what is this? 1 by 1 factorial d by dx of f of x, g of x evaluated at x equal to 0. Okay, so this is what you have. So what do you get? Differentiating by parts. So 1 by 1 factorial, okay, d by dx of f of x into g of x, okay, evaluated at plus 1 by 1 factorial f of x into d by dx of g of x okay. I will write down for the first term, then we can write down similarly for the second term. So let us write this. So what I will do is I will just write this as 1 by 1 factorial df by dx, okay, evaluated at x equal to 0 into g of 0. Can I write like this? G of x evaluated at x equal to 0. I am simply bringing it into the notation of differential transform. So 1 by 0 factorial, which is 1. So you have d0 by dx0, no derivative. Okay, so it is just g of x. So evaluated at x equal to 0. So in the notation of the transform, so what can I write this as? When I transform, just recollect this. When I transform when I transform y of x, what is happening? Small y becomes capital Y. This x becomes k. That's exactly what I have done here. Okay, k equal to 1 here. So small f becomes capital F. So likewise, what can I write here? G of 0. So what can I write the second term as? This one. So f of 0. Okay. So this is what you have. So which means I have f of 1 g of 0 plus f of 0 g of 1. Okay, this is what I have. So this is equal to, okay, let us see this. K equal to 0 to 1, f of